OpenAI is lowering costs for some of its models.
OpenAI has made its cheapest model even cheaper.
It is July 30th, 2026. Inside the most highly valued artificial intelligence company on Earth, someone just hit the panic button. Without warning, OpenAI releases an update that violently cannibalizes its own business model. They announce an 80% price cut to their GPT-5.6 Luna tier. The cost to process 1 million tokens, a metric that used to cost dollars, sometimes tens of dollars, plummets to just 20 cents. To the casual observer, it looks like another pricing strategy, a win for consumers. But to anyone watching the balance sheets of Silicon Valley, this is a distress flare. For years, the industry consensus was simple. The company with the smartest, largest foundational model held the monopoly. The intelligence was scarce, therefore the margins were astronomical. Proprietary labs structured their entire empires and raised capital at trillion-dollar valuations on the assumption that they could charge massive premiums for access to their minds. But OpenAI didn't slash their prices by 80% because they wanted to. They did it because they had to. Over the course of just a few weeks, enterprise customers were quietly migrating massive volumes of data away from proprietary APIs. Fortune 500 companies were realizing they could process millions of customer support tickets, extract database rows, and run complex agentic workflows for pennies on the dollar. The monopoly on artificial intelligence was collapsing. But what actually broke the monopoly wasn't just a single competitor. It was a massive industry-wide realization that the greatest bottleneck in artificial intelligence wasn't the math. It was the traffic jam inside the silicon. And the moment the industry figured out how to clear that jam, the premium AI market began to vaporize in real time. To understand the crisis facing the incumbent tech giants, you have to understand the fundamental physical flaw of the modern graphics processing unit. The GPU is the engine of the AI boom. It is a mathematical marvel, but it suffers from a fatal limitation called the von Neumann bottleneck. Imagine a Michelin star chef working in a massive commercial kitchen. This chef can chop vegetables, sear meat, and plate dishes faster than any human alive. That chef is the compute core of the GPU. It can perform trillions of calculations per second. But there's a problem. The chef has a tiny cutting board, and the pantry is located on the exact opposite side of a massive crowded warehouse. Every time the chef wants to chop a single onion, they have to sprint across the warehouse, grab the onion, sprint back, chop it, and then run the chopped pieces back to the pantry before they can grab the next ingredient. The chef is the processor. The distant pantry is the high-bandwidth memory, or HBM. And that exhausting sprint across the warehouse is the memory transfer. As AI context windows expanded from a few thousand words to millions of tokens, the attention mechanism of these models started requiring quadratic increases in memory access. The processor had to read massive matrices of data from the distant HBM, write the intermediate math back to the HBM, and then immediately read it again for the next step. The theoretical speed of the GPU was skyrocketing. But the actual speed of AI generation was stalling. The most expensive, highly sought-after chips on the planet, the NVIDIA A100s and H100s, were spending the majority of their time completely idle, waiting for data to arrive. This wait time is latency. Latency dictates how many users a server can handle at once, and how many users a server can handle dictates the profit margin of the company running it. For years, this hardware inefficiency made generating a single AI token artificially expensive. The proprietary labs were perfectly happy with this bottleneck. As long as inference was impossibly expensive and complex to run, no one could challenge their dominance. The high prices felt justified by the sheer cost of the hardware, but a quiet rebellion was brewing in the halls of academia and open-source infrastructure. Systems researchers began to look at the Michelin star chef sprinting across the warehouse, and they asked a very simple question. What if we just gave the chef a bigger cutting board? The solution began at Stanford University with an algorithmic breakthrough called FlashAttention, pioneered by researchers Tri Dao and Dan Fu. Instead of writing massive chunks of intermediate math back to the slow, distant high-bandwidth memory, FlashAttention kept the data strictly on the chip's ultra-fast, local memory, the SRAM. It chunked the math into tiny tiles, completing the entire calculation before ever sending the final result back across the warehouse. It was a masterclass in hardware-software co-design, but there was a catch. Implementing this kind of optimization required writing thousands of lines of highly complex CUDA code. CUDA is a low-level programming language, so unforgiving that even a minor error could crash a multi-million-dollar server cluster. The hardware was capable of running AI efficiently, but the software was too complex for most developers to wield. To bridge this gap, infrastructure companies began building abstraction layers. One of the most aggressive players in this space was Together AI, founded by a team of systems researchers. Their kernel team developed a framework called ThunderKittens. Despite the playful name, ThunderKittens is a weapon of mass optimization. It is an embedded coding library that takes standard 1,000-line CUDA kernel code and compresses it into a highly optimized 100 to 200 lines. It automatically manages the optimal layout of memory. It perfectly aligns the math with the specific physical architecture of NVIDIA's chips. It completely shields the developer from the manual allocation of shared memory, allowing the computation and the data movement to overlap perfectly. The chef is no longer waiting for ingredients. The ingredients are being handed to them the exact millisecond their knife lifts from the board. The financial implications of this optimization were immediate and catastrophic for the incumbents. By fusing these optimizations into the kernel level, infrastructure providers could reduce the time to first token in real-time applications by over 3 times. When your servers run 3 times faster, you can serve 3 times as many customers on the exact same hardware. Your capital expenditures drop, your operating costs plummet. The fundamental physics of AI inference had been solved. The operational cost of serving generative AI was collapsing by up to 85% across the board, but speeding up a single chip was only half the battle. To truly commoditize the AI market, the industry needed to conquer the network. Imagine a massive toll plaza on a superhighway. In a traditional cloud network, the traffic cop assigns lanes based on static percentages. 25% of cars go to lane A, 25% to lane B, and so on. But generative AI traffic is unpredictable. One user asks for a 2-word answer. The next user asks the AI to read a 1,000-page legal brief. If lane A gets hit with 3 massive legal briefs, it jams up. Meanwhile, lane B sits completely empty. In standard server networks, this static routing leads to massive pipeline bubbles, which means wasted time and wasted money. To achieve maximum margin destruction, infrastructure providers abandoned this model entirely, implementing what is known as dynamic, capacity-aware routing. They strictly separated the identity of the AI model from the physical hardware running it. When a user sends a prompt, the router doesn't look at static percentages. It looks at the real-time mathematical availability of every single GPU in the entire network. If a server goes down, or if a deployment is in the middle of a cold boot, its effective capacity instantly drops to 0. The traffic seamlessly flows to active servers. No dropped requests, no backed up queues. This means enterprise operators can spin up servers, test new models, and destroy them based purely on traffic demand. The infrastructure becomes entirely disposable because the system ensures that no single GPU is disproportionately saturated. The network achieves near-perfect utilization. With the hardware running at maximum efficiency and the network routing traffic flawlessly, the true cost to run an AI model was suddenly approaching 0. And that brutal efficiency gave birth to a financial empire that almost no one outside of Silicon Valley saw coming. Consider 2 artificial intelligence companies both founded in the exact same year, 2022. The first is 11 Labs. You've almost certainly heard of them, or at least heard their technology. They built the highly visible consumer-facing AI that clones voices for TikToks, video games, and audiobooks. By mid-2026, their cultural hype had pushed them to an $11 billion valuation, pulling in around $500 million in annual revenue. But the second company, Together AI, operates in near-total darkness to the average consumer. They don't have a flashy app. You can't ask their website to write a poem or generate a deepfake. Yet by early 2026, this invisible infrastructure giant was crossing a staggering $1 billion in annualized revenue. How? By acting as the toll booth for the entire open-source AI ecosystem. They built a lethal 2-pronged business model that targeted the exact weaknesses of the proprietary labs like OpenAI. Prong 1 is the serverless API. For independent developers, Together AI sells access to open-source models by the token for mere pennies. Because their hardware optimization is so ruthless, their gross margins sit around 45%, meaning they print cash even while undercutting OpenAI's legacy prices by orders of magnitude. But prong 2 is where they capture the Fortune 500. Massive corporations are terrified of vendor lock-in, the idea of permanently renting their corporate brain from a company like Google. So Together AI leases them dedicated infrastructure. A bank or a hospital can rent a private single-tenant cluster of NVIDIA H100s or next-gen Blackwell chips. Using an incredibly cheap technique called LoRa, the enterprise can fine-tune an open-source model directly on their highly secure private data. The corporation walks away owning their model weights. Their intellectual property remains theirs. This dual business model turned together AI into an absolute financial juggernaut. But perfectly optimized plumbing is useless if you don't have water to run through it. The market had the cheap infrastructure. Now it needed an open-source model capable of rivaling the trillion-dollar giants. In April 2026, the dam finally broke. Up until this point, proprietary labs like OpenAI justified their high prices with superior reasoning capabilities. Open-source models were good, but they couldn't handle massive million-token context windows or highly complex agentic tasks. Then came DeepSeek V4. Released in the spring of 2026, DeepSeek V4 represented the exact historical moment where open-weight architecture and hyper-cheap infrastructure perfectly converged. DeepSeek V4 Pro is a monster, a 1.6 trillion parameter model. But it uses a highly advanced mixture of experts architecture. Think of it like a massive university. You don't ask every single professor on campus to solve a basic math equation, you just ask the math department. When you query DeepSeek V4 Pro, it routes the traffic so efficiently that only 49 billion parameters are active for any single word generated. Even more disruptive was the V4 Flash variant. It boasts a million-token context window but utilizes a mere 13 billion active parameters per token. DeepSeek achieved this not through brute force computation, but through DeepSeek sparse attention. Instead of memorizing every single word in a million-word document, the model compresses the vast context into coarse summaries, only applying deep, dense focus to the mathematically relevant regions. It dropped the computing requirements for a million-token prompt to just 27% of previous models, and because of its tiny active parameter footprint, V4 Flash was phenomenally inexpensive to serve. DeepSeek's official API pricing plunged to 14 cents per million input tokens, but when you combine DeepSeek V4 with the ruthless kernel optimizations of the new infrastructure layer, the economic moat of the entire AI industry evaporated. Platforms began implementing caching systems that remembered previous inputs for systems like AI agents which constantly reread their own system prompts. This is revolutionary. The cost for cached inputs on premium open models dropped to 20 cents per million tokens. A production workflow that would have cost an enterprise tens of thousands of dollars on a proprietary model was suddenly costing $9,000. The barrier to entry for state-of-the-art AI was gone. DeepSeek had provided the intelligence, and the infrastructure layer had provided the scale, and the fallout landed directly on the desk of OpenAI. Which brings us back to July 30th, 2026. It is crucial to understand that OpenAI did not cut their prices because of one single startup. Together, AI and their kernel optimizations were just one piece of the puzzle. The true threat was the ecosystem itself. By mid-summer, Chinese-developed open-weight models, spearheaded by DeepSeek, were claiming over 66% of all token volume on aggregated routing platforms. Fortune 500 chief information officers were looking at their budgets and realizing they were burning millions of dollars on proprietary API calls that could be executed at an 85% discount on the open market. The intelligence was no longer trapped behind a walled garden. OpenAI had no choice to prevent a mass exodus of their enterprise token volume. They structurally recalibrated their entire pricing model. They bifurcated their GPT-5.6 family. They left their flagship reasoning model, Sol, untouched at $5 per million input tokens. It was reserved for the extreme frontier of intelligence, deep mathematical reasoning, and long-horizon coding, where open models still faced friction. But for the commodity layer of artificial intelligence, the everyday tasks like text classification, data extraction, and customer service routing, they slashed the GPT-5.6 Luna tier by 80%. Down to 20 cents per million tokens, OpenAI's PR department spun it as a victory. They cited newly discovered infrastructure efficiencies, but the market understood the truth. When an incumbent market leader slashes prices by 80% on a model launched merely 3 weeks prior, it isn't an act of generosity. It is an act of sheer competitive terror. The pricing power of the industry had irreversibly shifted from the seller to the buyer. OpenAI was reacting to the undeniable reality that their commodity intelligence was no longer a scarce resource. For the first time, intelligence was approaching the economic baseline of electricity. And when intelligence becomes as cheap and ubiquitous as electricity, you stop worrying about your electric bill and you start building factories. The true financial unlock here isn't just saving money on chatbots. It is the birth of the tokenized agent economy. Historically, true AI agents, programs that think, plan, browse the web, and execute tools on their own, were too expensive to run in production. They require continuous internal monologues, looping over their own thoughts again and again. Under the old pricing models, a fleet of autonomous agents could bankrupt a startup in an afternoon. But at 20 cents per million tokens, the math changes entirely. By deploying custom schedulers that eliminate memory thrashing, enterprises can now afford to let autonomous agents loop continuously. They can think, correct themselves, and solve complex multi-step problems without triggering budget alarms. This architectural decoupling also solves the final hurdle of enterprise adoption: data privacy. Because capacity-aware routing separates the model from the physical hardware, inference can be fluidly routed across the globe to wherever compute is cheapest or most available. Projects are already utilizing trusted execution environments to guarantee that corporate data is never logged or retained during the generation process. Enterprises no longer have to surrender their intellectual property to centralized labs. They can lease dedicated hardware clusters, fine-tune an open-source model on their private data, and deploy bespoke intelligence that they own completely. The architecture of the artificial intelligence industry has undergone a permanent realignment. The ultimate economic moat was never just the mathematical intelligence of the models themselves. It was the mechanical inefficiency of how they were served. By solving the GPU memory bottleneck, by abstracting silicon physics, and by open-sourcing frontier intelligence, the massive margin has been completely stripped from the token. The era of the foundational model API premium is over. The era of commoditized, infinitely scalable intelligence has just begun. What happens next when compute becomes virtually free? The ripples of this shift will dictate the next decade of technology, but who do you think is positioned to win in this new era of cheap intelligence? Let me know your thoughts in the comments below, and if you want to keep exploring the unseen mechanics driving the tech industry, make sure to subscribe. We're just getting started.